Okay, so this one goes out by request. This is the birthday paradox. Suppose there is a room with 6 people in it. What's the probability that at least 2 share the same birthday? Well, I wanted to mention that in my previous podcasts, I've demoed how to go to Wolfram Alpha, and you just key in the words birthday paradox. It's a famous problem. And you just use the app or the website. You tell it the number of people in the room, 365 days in the year, and then it will tell you the probability that at least 2 share the same birthday is about 0.04. But many of my students are wondering, how would I do that myself with just a handheld calculator, let's say? So let's go back. Okay, so the probability that at least 2 share the same birthday is really, if you translate that, at least 2 means 2 or 3 or 4. And remember, there's 6 people in the room. Or 4 or 5 or all 6 share the same birthday, right? But what's the opposite of that? Well, 2 or 3 or 4 or 5 or all 6 of them, the opposite of that is none of them having the same birthday. So we're actually going to use the complement rule. So the underlying concept here is the complement rule. So the complement rule says that rather than directly calculating this, we'll take 1 minus the probability of the opposite of this. So again, the opposite of 2 or more having the same birthday is none of them having the same birthday. So instead, we'll do 1 minus the probability that none share the same birthday. That's the trick. So I'm actually going to flip ahead here. So remember, keep your eyeball on the answer, 0.04. Okay, now let's zoom in on that. So 1 minus the probability that none share the same birthday. Well, just think about that. 1, 2, 3, 4, 5, 6. All right, let's just say this first person has a birthday that's August 2nd. What's the probability that the guy or girl next to him doesn't have his birthday? Doesn't have his birthday. So you're thinking 364 out of 365. And then what's the probability that the person sitting next to them doesn't have either one of their birthdays? Well, hopefully you're thinking 363 out of 365. And the person next to them doesn't have any of their birthdays. And now you're starting to notice something. The person next to them, and so on and so forth. So you do this, think of this as person 1, person 2, person 3, person 4, person 5, person 6. Now, if you just have a basic handheld calculator, and that you would compute this, so you would multiply all this out, and then you would take 1 minus that. Now remember, that first person's birthday is sort of, we fixed them at, August 2nd. So you really just end up multiplying all of this, right? And then, like I said, taking 1 minus. And you will arrive at approximately 4%, okay? But now if you're sort of a deep thinker, you might want to generalize and say, okay, well, what then? Let me develop the formula for n, when there's n people in a room, rather than just 6 people. What about 20 people, 30 people? So to generalize, I'll just mention, that's a deeper thought. But to generalize, think of this for pattern recognition. Notice the pattern, 364, 363, 362, all the way down to 360. Consider this first person 365 out of 365, because there's a 100% chance that they have their own birthday. So just for pattern recognition, consider it like this. And 365 out of 365 is just 1. So you could consider this, multiplying 1 by all these decimals is 1 times anything is itself. So anyhow, let's go ahead and record this and see if we can see a pattern. So a lot of, coming up with formulas is pattern recognition. So I think I can get you to say part of the pattern. Okay, let's count. Remember, there were 6 people in the room. Okay, I'm going to switch to a different color here. 1, 2, 3, 4, 5, 6. How many 365s are there? There's 6 of them. Aha, so, and you're multiplying, so 3, you're figuring 1 minus something, and you're noticing on the bottom 365 to the nth power. So n is 6 in this case, so you're noticing 365 to the nth. Let's hold that thought. Okay, so just as a reminder, you could just simply type this all out in your calculator, but like I said, if you had a room with 25, 30, 40 people in it, that'd be a lot of stuff to type in your calculator, so we like to generalize with the formula. And we have the bottom part. We know that's, 365 to the n. Now up top, you're noticing 365, 364, 363, and so on, and you're feeling like it has something to do with factorial. And it does. It turns out it would be 365 factorial over paren 365 minus n, whole thing factorial. And if you think about why that is, in our situation here, we were letting n equal 6, right? So if you take 365 minus 6, you get 359. So if you just think about it schematically here, 365, 364, 362, as if you were going to write out 365 factorial, 361, 360, and then you'd eventually hit 359, and so on and so forth. And then if you were going to write out 359 factorial, it'd be 359, 358, 357. But what you're noticing is that in time and space, all of these components would cancel with all of these components, and you would indeed be left with these numerators up here. So it is sort of up a notch in thought for students to think about this as being the formula. Now that's a complex fraction, so I am going to clean it up. So it turns out if you're looking for a formula for this sort of, we can generalize for a room of n people. So now, if you want to change it to 20 people, 30 people, 40 people in a room, for a room of n people, we could say that the probability that at least 2 share the same birthday would be 1 minus, and now we have this expression here that will take care of this expansion. So 1 minus 365 factorial, and then I'm going to clean up that complex fraction. So 365 minus n whole thing factorial times 365 to the n. And I'm going to go live cam here. What I did was, I'm going to go live cam here in a second. What I did was I typed this whole expression into Wolfram Alpha. You could do it on a calculator as well, but into Wolfram Alpha, and I let n equal 6 just to show that the answer is indeed 0.04. So check, I'm just going to write here, check to see that it's 0.04. All right, so let's take a look. Here I'm going live cam on my computer here. Okay, so you see I typed in that expression, and then I said for n equals 6, and you see it computed it, and it says about 0.04. All right, so I'm going to go back to the previous slide. And again, I'll let you sort of rationalize in your own mind, again, how we took all of this and expressed it here. So, and I'm just going to highlight that. All of this gets expressed in general form here. Okay? So good luck out there. And like I said, if you have a small sample, I was going to say if you have a small sample like n equals 6 or 5 or 4, it's just as easy to type all this out. But when the class size gets larger, you have to generalize. Good luck out there.